A DC motor is a device that looks like this, and it takes power from two wires like this, from a power source like this, a battery, and turns it into mechanical motion. But how fast does it spin? How much torque does it apply? How efficient is it? How can we know the answers to these questions? These are the subjects, the topics of this next sequence of videos. So this is the starting point of our model of a motor. Here's the body of the motor, and here's the axle of the motor, and the output of the motor is this angular velocity of the axle given by omega here, and a torque given by T here. And so the question is, how much of each of these do we get as a function of each of these? Voltage going into the two wire terminals of the motor, and the current going in. So let's start for how to understand this with, let's say, the simplest version of a motor, which is depicted here in this left column here. It consists of a single loop of wire through which current is flowing. And the Lorentz law tells us that current going through these two segments of wire results in forces. And so we can draw, using our right-hand rule, if the current is perpendicular to the magnetic field, we get a force that is perpendicular to both of those two. And so we get, I didn't want to change that color there. I wanted this to be this. Okay, so we get one force on this little segment that looks like this. And we have another force on this little segment that looks like this. And it turns out you can show for yourself that the rest of these segments here have no effect on the force. So we have these two forces that collectively result in a torque that causes this loop to rotate around this angle like this. And another way, maybe more helpful way to think about this, is that the current going through this loop also creates its own magnetic field distinct from this magnetic field. So I'll draw that magnetic field that this loop is creating. So I'll call it B here. So another way to think about this, and it's equivalent to these two forces acting on those two segments of wires, is that there is a torque applied around this rotation axis of this loop that acts to align the magnetic field that it creates to the external magnetic field caused usually by a permanent magnet placed near this coil. Okay, so if you were to plot that torque as a function of this rotation angle of this loop around this axle, you'd see something like this, where as you vary the angle on this axis, you get more or less, we'll call it Tm for magnetic torque. And so what this picture here shows is this point here. The magnetic torque is at its peak when it's this misalignment of the two magnetic fields is strongest. And then if you were to allow it to rotate, it would go down this this line here, and then here corresponds to the location where there's no more torque here. The torque is 0, and that is when the magnetic field of the loop is in the same direction as the external magnetic field, so there's no torque. And then what happens in this case is if you keep rotating the coil even more, the torque reverses direction, and you end up with a counter torque that drives it back to an alignment to here. This kind of corresponds to the intuitive intuition you might have that these two things want to align their magnetic fields, and as you rotate this back and forth, it will drive it back to this point. So this is an equilibrium of this system, and because of that, you can imagine this does not do what we need to do in terms of continually rotating, which is what we want our motor to do. In order to get continuous rotation, we need a trick, and that trick is known as a commutator, as shown in this column here. In a commutator, you additionally attach to this loop a a ring that's physically attached and electrically attached to one end of the ring, and a second ring that covers the other kind of half rotation connected to the other end of the loop here. I'm going to change terminology here from this point on to a coil instead of a loop, because often in motors it's more than one loop here, and the more turns you get of the coil, the stronger the torque is. Okay, so the ring here is electrical conductor, usually copper, and it rotates along with the coil here. And then in addition to this commutator that rotates, we have these two electrical contacts that are also metal that touch this ring. And these are known as brushes, and they allow current to pass from this fixed source out here onto the ring and then through the coil here. So the brushes are fixed, but they're always making electrical contact. And if you design where these gaps appear correctly, what you can get is the torque to be positive, and then just as you reach this point here, which is known as a commutation point, if you have the gaps in the right place, you switch the direction of the current going around this coil. And when you do that, suddenly you get positive torque at this point instead of negative torque. And if you're already spinning, if you start it somewhere in here and it starts spinning, you'll pass over this zero torque point and continue spinning like this. And then once you've got that going, you're continually rotating. And with this commutation, you were able to get continuous rotation. So if you take the time average of the torque, this green line here, you get some ripple in the torque, but on average you get an average torque, something like what this looks like here. You can imagine that torque, which is a time average torque, is going to be proportional to the current going through this loop here, and that proportionality constant is called K, a motor torque constant, and we're going to revisit this K several times. But the thing I want to mention about this K now is that this K kind of characterizes the motor. The bigger the motor, the bigger the K, the more turns of the in the coil here, the bigger the K, that sort of thing. So this kind of characterizes let's say, the strength of the motor here. So with this, we have now a system that we can generate continuous rotation. I want to mention there's another category of motor that's becoming more popular these days because it has some benefits at the expense of complexity, and that's a brushless motor. The same principles apply for a brushless motor. The big difference is that there's no brushes, and instead a computer turns on and off the coils. And instead of having the coils spin, it turns out that in a brushless motor, usually the coils stay fixed and the magnet spins instead. And then a computer senses voltage ripple coming through the terminals of the coil, and they use that to determine when to turn on and off the different the coil. This requires a little bit more complexity because now you need transistors to turn on and off the coils, and you need a sensor. But in exchange, you get longer lifetime because these brushes tend to wear out with time, and you also get more efficiency because you don't have the friction of this brush scraping against the motor here. But it is more complicated. Next, let's talk about a model here, and the model we derive is going to apply for both brushless and brushed motors here. Call it a dynamic model here. Okay, so let's start on the left with a source, and our source is going to be and this is the electrical drawing of a source. It's going to be either call it VS for voltage source. Or alternatively, we're going to consider IS, which is a current source. And these have costs and benefits associated with each of them. Over here on the left, we're going to start by including the model of the coil, which is going to consist, pretty good model for this, is an inductance in series with a resistance, and we'll call the inductance L and the resistance R. The next thing, we're going to plug this into what's known as a transducer, and this is something you may not have seen before. We'll derive the equations of this transducer. A transducer is a device that, let's say, transduces power from one domain to another here. I'll call this a transducer here. This is a symbol we're going to use for the type of transducer that lives in the electric motor here. And this transducer is this proportionality. Part of it is going to be this. The torque coming out of the coils is proportional to the current going in. So here's the current going in here. Let me make that red. And here is, I'm going to use the same color, the torque coming out. Okay, so I'm going to use this so-called mobility analogy where over here, this is the electrical domain. And over here is the mechanical domain. In this analogy, we're going to think of torques and voltages like currents, and torques and velocities like currents and voltages. In particular, we're going to treat torques like currents and velocities like voltages here. So here we have a current coming in and we have a torque coming out, and so the relation for this transducer is this equation we derived earlier, Tm equals Ki. So given a current going in, this is how much torque comes out, and it's the proportionality constant is this motor torque constant K. Okay, and now we're going to jump over into the mechanical domain here on this side here, and we're going to consider various kind of aspects to the motor here. First, on the mechanical domain, I'll draw it over here. The first kind of thing that pulls off the torque coming out of the transducer is the inertia of the rotor here, and which I'm going to model as a capacitor, and the capacitance is equal to the moment of inertia of the rotor. This connects to that ground there. And then we have some, I'll just call this rotor inertia. We also have a angular velocity dependent drag, which in the electrical domain, I'm going to draw as a resistance. I'll call it RB, and that is equal to 1 over the drag constant B here. So if you have a viscous damping drag, often in mechanical you use the letter B. So RB is 1 over that. This is one of just the differing conventions for how different domains usually label things. And the last one is a pure source, which I'm going to draw like this, a torque source. I'm going to call this TC, and this is so this is a velocity dependent drag, and this is a Coulomb drag, TC, which is also due to bearings and or brushes, that does not depend on RPM. So over here is the coil. It's too hard to read, different color. Here's the coil. And over here, this is, I'll just call this drag here. Okay. So there's the two sources of drag. And then lastly, we have over here our load. And maybe this is an inertial load, maybe it's a resistive load, maybe it's some combination of those, who knows? we don't really care here. We just know that there is a load here. Okay. So this is electrical domain, and we've turned everything in the mechanical domain into kind of electrical equivalents for convenience here. And then finally, we have the key thing here. Using the analogy of current here, this torque goes in here. Some of it gets pulled off in all of these places, and the amount of torque that remains we're going to call T. This is the torque that comes out of here. And also we have these nodes here. Here these nodes are voltages. Here these nodes are velocities. So the angular velocity here is omega, and just by electrical, this also omega here. It's the same thing because they're connected by a wire here. Okay. That's a drag, two drag sources and a rotor inertia here. Okay. Now, the next thing we want to do is figure out what this angular velocity omega is coming out of this thing here. If we know the current going in and the torque coming out, what's the angular velocity here? For this, what is omega, angular velocity? Well, to figure that out, we're going to use another property of transducers, which is that they conserve power. So transducer conserves power. Which is to say, the power going into the transducer is equal to the power coming out of the transducer. The power into the transducer is, what's the power going into a transducer? It is the, in this case, what's the electrical power? It's the voltage. I'm going to call that the magnetic voltage going into this transducer times the current here. Note, we haven't defined what this is. This is, in fact, this voltage here, Vm. There's a voltage here. This is V, by the way. And this is a different voltage than V because we have some voltage to drop across this coil, this inductance and this resistance. And this is what we're left here after this drop. This is the magnetic voltage here. So the product of the current going in there, and this current is the same here and here because of just loop laws, Kirchhoff's current law. The power going into this arrow here is the product of the voltage times the current, that's power in. And this is equal to the power out. And what's the power coming out of here? It's the product of the torque times the angular velocity. So Tm times omega here. Okay. Now, I'm going to write this here again. What is Tm? Well, I'm just going to use the motor constant multiplied times I. That's equal to Tm times omega here. And now I can cancel these i's, and I get that the angular velocity coming out of there is equal to 1 over k times Vm. Okay? So let's write that in here. This is the other part of this transducer equation. The motor constant appears again, but it's in inverse. So the angular velocity here is equal to 1 over k times this Vm, the magnetic voltage here. This V, so now we've got this relation and we got everything we need now to do some more analysis. Let me just briefly mention this Vm. There's a special word for it, and it's derived from historical times when before there was actually a word for voltage, and Alessandro Volta, the Italian physicist. So Vm is known as the back electromotive force. or EMF. Electromotive force is the word they used before they had defined the volt, and it's the same as a voltage, so it's the back voltage. So this is the voltage that arises in a coil when you start spinning it. It turns out when you start spinning this coil in this magnetic field, it actually develops a voltage here. The faster you spin it, the more voltage appears here. It is defined by this relation here. So you spin this really fast and you get more voltage here. Okay. So now there's a lot of stuff going on here, but it turns out you can learn a lot, and it's quite important to think about the steady state behavior of this system. So let's talk about what we mean by that here. So first of all, let's talk about the dynamics of this system here. So if you just turn on the voltage, like maybe you plug this motor into that battery, what happens? If you plot it as a function of time, where this is, let's say, the angular velocity and this is time here, what you see is that you have this slow build-up to some terminal angular velocity, terminal angular acceleration, and then you have kind of this S-curve, and then it slowly levels out like this. So you have these kind of different domains. The first thing that happens is this electrical, called the fast electrical rise. I call it response. And you can have a time constant electrical associated with it, and that time constant turns out to be the inductance of the coil divided by the resistance of the coil. Then you have the slower response here. Goes to about there. This is a slow mechanical response. With a mechanical time constant equal to the so-called RC time constant, this resistance times the capacitance here. And it turns out when you have this resistance and you reflect it through this transducer, it looks like this R times C, but you also have this constant K squared that appears here. I won't derive that here, but that's just how it comes out if you derive it yourself. Okay, so we have this kind of two dynamic responses to these two kind of systems. And then finally you have this kind of steady state behavior. Which is kind of the asymptotic behavior. It's steady state. The motor just reaches a steady state velocity here. And what we're going to do now is focus on this steady state behavior. In practice, if you were doing control, you might want to know something about the speed of these dynamics, and you could characterize that with these two time constants here. But a lot of what you care about is the steady state behavior. So let's focus on that right now. Steady state model. In the steady state model, inductors turn into wires, and capacitors turn into open circuits. So we can draw a kind of steady state model with these transformed. And one other thing is a resistance we're gonna remove the complexity of the transducer and do everything in the mechanical domain over here. So in this case, we're also going to make R in the mechanical domain becomes R over K squared transduction. Okay, so that looks like a source again over here, drawn as a circle, an ideal source, driving a resistance R over K squared. And now we have our node here, which has angular velocity omega and the torque Tm coming through here. And then it's connected to these sources of drag here. We have the we've left out the rotor inertia because which looks like a capacitor, because becomes an open circuit, so we don't have the inertia appearing here. As you might imagine, steady state, rotor inertia doesn't matter anymore. But we can't neglect this this RB, and we also can't neglect this Coulomb friction from the bearings either. And of course, we still care about the load here. There's that. Okay, and then this all is also tied to ground. Okay. So we still have our torque going into the load here. We have our Tm coming out of here. And over here, the source. Now, by eliminating the transducer, we have a source of two different types. It can be either a velocity or a current source. So let's see how I wrote it up here. Now we're going to have we're going to consider either omega s equals 1 over k vs. So this is a velocity source. And so if we were to have a voltage source here, the velocity source becomes the voltage source divided by k. Or we'll consider the other possibility, which is a torque source, Ts. And that torque source is equal to k times Is, torque source. In other words, if we're driving our motor with a velocity source, then that in this case becomes omega s or Ts here. It either becomes a velocity source, an ideal velocity source, or an ideal torque source appearing here. And note that these ideal sources are what you've seen in electrical engineering, same idea. It's the velocity here for a velocity source is always going to be whatever is omega s, regardless of how much torque you draw out of here. Or if it's a torque source, the torque going through here is going to be the same regardless of the velocity that this node is spinning at here. Okay, so we have these two cases here. We're driving it with a voltage source or a current source, and those become velocity sources or torque sources, respectively. So let's consider current control. And then later we will consider also voltage control, which is the second case. So current control, and in current control, the source it's a torque source, and that's equal to k times the current you are supplying the motor with. So to analyze what's going on there, we use a node equation. At this node here. So the torque coming in is equal to all the torques coming out, is equal to T, let's see, T, I'll call it TB here going here, plus the torque going through this one here, TC, plus TM. Sorry, T here, this the torque going into the load here. Or in other words, T is equal to Tm minus Tb minus Tc. So in many cases, these two sources of drag, which are the same sources of drag here, can be assumed to be small. And in which case, we want to be aware of them, but we can sometimes neglect them. And here it actually becomes quite informative to think about if you just neglect them. And what you get is that T is, in that case, roughly equal to Tm. And Tm is, well, any torque coming through here, that's a Ts, is going to be the same as Tm because it's just by how current or torques work, is equal to K times this current source coming in. And so what you should see from this is that torque is proportional to IS. And more generally, it turns out that it isn't just if you have a current source, but if you have any current going through the motor, as we saw over here by the same idea. Here's a current going through here. Here's this original equation, and it kind of appears the same way there if you neglect the drag. If you know the current going into your motor, or any, even if it's not a current source, if you know the current going into your motor, you know the torque coming out of it. And what this means is if you have control over this, you can control the torque directly. So in other words, motor can behave like a pure current, behaves nearly like an ideal current source. Sorry, not current source, torque source. And that way you can program it to do whatever you want. You can make it behave like a Coulomb friction or viscous drag or any other thing you want to do with it with control. That can be very handy for control because now you just have a torque source. So that's kind of the good news, let's just say. But the bad news is that this costs money. Current sources tend to be more expensive and more complicated and less efficient. And much more often, you have a voltage source instead. So if you're lucky enough to have the luxury to have a current controller, you probably want to use it, your motor in this way and drive your motor with a current source so it behaves like a torque source, and then you can do quite simple analysis. But more often, you are actually going to be driving your motor with a voltage source instead, which is much simpler. In which case, the dynamics are much more complicated, and in the next video, we're going to talk about this other case here, which is voltage control. And so we'll stop there and pick that up in the next one.